Okay, welcome to lesson 3 of chapter 2. So this is 2.3. I'm only going to be doing a select portion of 2.3 just because I like to teach it separately. I think they're quite different from the rest of 2.3, so we'll get to that later. But for now, we're going to be looking at diffusion and osmosis. Those are two different processes. Before we get into that, though, we're going to need to learn what concentration is. So concentration, by definition, is the number of molecules of a substance in a given volume. So in my example that I have on the slide, I've got two different boxes, each with a given volume. So in this first box right here, I've got 10 different blue molecules. Let's assume that's water. And in this box, I've got 10 different molecules of water as well. So I've got a given volume for both of these boxes. So let's say we are going to be looking at orange juice. If there is a low concentration, I'm looking at the number of orange juice compared to my volume that's there in that box. So I've got 3 different molecules of my orange juice as opposed to the 10 molecules of water that I have there. That's what is a low concentration. In a high concentration, I've got these 10 molecules of water, but let's say I've got all of this orange juice. There's a lot more of that orange juice than compared to the low concentration scenario. So in a high concentration, there's a lot more of the orange in comparison to the given volume, rather than in our low concentration when there's very little of that orange compared to my given volume. Okay, so I've got a high concentration, I've got low concentration. Keeping these in mind, I can explain what diffusion is. So diffusion is the movement of a substance from an area of high concentration to an area of low concentration. So let's take a look at an example right here. So I've got this beaker, and I've got a bunch of water in there, and I've got some red dye. In between those two areas, I've got a thin film, which will allow for those particles of dye to travel through it. So what's going to happen if I leave this particular beaker, I'm not moving it, I'm not shaking it, I'm just going to leave it as is. Over time, what I'm going to find is that these red particles, let's take a look at the second beaker here, these red particles are going to go from an area of high concentration to an area of low concentration. So there's a lot more of this red here to begin with, but it's going to start moving over to the other side. Eventually, it's going to appear to us that there is about the same concentration of red on either side of our film. So what we started off as to have a high concentration and low concentration is going to have about the same concentration. An important thing that I want you to remember here is that these particles have not stopped moving between the film. So they are still moving from left to right, and then right to left. It's just that the rate of diffusion is pretty much the same on both sides. So it appears to our eye that it's exactly the same. They're not moving anymore. They are still moving. It's just moving at an even pace, which means that those concentrations are maintained. Okay, I'm going to show you a video just to put it in a different, or just to explain it a little bit differently. This is a video by the Amoeba Sisters. It's on the PowerPoint. If you want to click to it and then watch the full video, feel free to do that. In this particular lesson, I'm only going to be showing you from 0 to 241. Okay, so I'm going to play that.
Have you ever heard of the ick? The disease, that is, that can afflict aquarium fish? I will never forget the first time my fish caught ick. Well, it's called ick. It stands for this. So, ick it is. It's actually caused by a protist, a parasitic one. In our ecology video, we talk about parasites and how parasites benefit while causing harm to their host. And in my case, it was all of my beloved fish. Well, okay, technically it affected Gertrude first, but then it spread because it is a contagious disease in fish. Ick typically causes these white dots. It gets on their fins, on their bodies, on their gills, all over. It can even be lethal if not treated. So it's bad news, and being a guppy enthusiast, I was really worried about all of my guppies. This is not a video about parasites. This is a video about diffusion. So you're probably wondering, how is she going to connect diffusion to this parasitic protist disease? Well, it's because of the treatment. You see, there is a commonly purchased treatment for the disease of ick. One common treatment option contains an antiparasitic called methylene blue. Its name is not misleading, it is quite blue. The directions on the back of the medication outlined how many drops to add per gallons of water, and I watched and tried to encourage my fish to swim towards the medicine, but they were panicked, maybe because a portion of their water was changing colors, but also probably because of the kid trying to get their attention to swim towards the medicine. But you know what I didn't know then? I didn't need them to swim over there. The blue drops would spread on their own in a process known as diffusion. Diffusion is when the net movement of a substance travels down its concentration gradient. That means it moves from a high concentration to a low concentration. When the methylene blue drops were added into the water, they didn't just sit there. The molecules traveled in the water through diffusion. The high concentration of molecules, which is where they were dropped, spread to areas of low concentration in the water. Pretty soon, the water had a uniformly blue appearance as the molecules eventually are evenly dispersed. This was very important for treating my fish because the treatment reached all of them, and they soon got better. Diffusion doesn't just happen in water. For example, it occurs if you spray an air freshener in the air. The net movement of molecules travels from an area of high concentration of the air freshener to a low concentration of the air freshener. Pretty soon, it's likely others would smell the air freshener, even if they were quite a distance away. Now, I want to mention...
Okay, so that's where I'm going to stop. So that was a pretty clear video. If you want to watch the rest of it, just go through the PowerPoint and then you should be able to find the link to it. I'm going to keep going for now. And I'm going to talk about some factors that affect the rate of diffusion. So we talked about diffusion, it's movement of high concentration to an area of low concentration. But how faster? What is the rate of diffusion? And what are some things that change that? So firstly, there's temperature. So the higher the temperature, the greater the rate of diffusion. If we take a look at that red dye experiment, I guess, that we did a little bit earlier, if you do that same process in hot water versus cold water, you'll notice that the rate of diffusion is a lot higher in the hot water. And that's simply because there's more energy in hot water, so those particles have a lot more energy when the water is warmer, which allows for it to move a little bit faster. Concentration difference is the second factor that affects it. So the greater the difference, so the more drastic the difference is between the high and the low of our concentrations, the more rapid the rate of diffusion is going to be. Okay, and lastly, we've got diffusion distance. So the shorter the distance the substance has to travel, the greater the rate of diffusion. Okay, these are just 3 different factors that affect the rate of diffusion. There's a bunch of different ones. For now, I just want you to focus on temperature, concentration difference, and diffusion distance. Okay, we're going to move on to our second process, which is osmosis. So diffusion was an area movement of a substance from an area of high concentration to an area of low concentration. The key difference in osmosis, it's the movement of water. So the definition of osmosis, the movement of water from where there is more water to where there is less water. So in this case, I've got my scenario here. I'm just going to draw on it. Maybe I'll use yellow. Okay, so say for example, I've got a scenario here with 2 different concentrations, right? Okay, and I've got this barrier in between. This barrier may allow for the water to pass through, but maybe not for the red substance. So the water in this case is going to be the blue dots, and then the red substance is going to be, let's say, dye. Okay, so it's anything else. So what this is going to do, this barrier allows for the water to pass through, but not the dye to pass through. So if the dye can't go from an area of high concentration to an area of low concentration, what's going to happen in order for those concentrations to sort of balance out is that the place where there's more water, that water is going to move over to the other side. It's going to go from where there's more water to where there's less water. Okay, so eventually a lot more of those water particles are going to move from one side to the other. Okay, how do we know where it's going? Where it's going to move from? It's going to move from where there's more water to where there's less water. Okay, and lastly, just a point about both diffusion and osmosis. These are both means, or these are both methods that take place as passive transport. So passive just means that it just happens as is, right? So I'm not putting any energy to it. I'm not, or you as a scientist or whoever is not doing anything to cause diffusion or osmosis. They just happen without using any energy. Okay, so just like that beaker, to start off with the red dye, if I just leave it as is, it's going to still happen. Diffusion's going to happen. I don't have to do anything for it to actually take place. Okay, and that is pretty much it. There's just one question for you to do for homework, and that's our lesson. Bye.